Hello, and welcome. I'm Tess. I'm a developer and a data scientist at Microsoft. And I've been spending a lot of my time before doing data science and machine learning and doing debugging in .NET. So what I found, though, is that looking at large dumps and figuring out bugs and kind of looking at patterns is exactly what machine learning is too. You look at large amounts of data and try to find patterns in it. So a typical problem that you might run into in machine learning is a classification problem. In this case, we're trying to classify these pictures. One is of a muffin and one is of a chihuahua. How many of you think that this one is the chihuahua muffin, or the muffin picture? Okay, one. That's brave. I think most of you probably know that this is a chihuahua, right? You think it's a chihuahua? So why do you think it's a chihuahua? What makes you kind of come to that conclusion? Okay, it looks like a dog, like it has ears, it has eyes. Yeah, so some features that you can kind of distinguish from that one that doesn't exist in a muffin case. So as humans, we tend to learn by kind of using all our experiences. So we've seen enough dogs or chihuahuas so we can distinguish that this is a chihuahua. Or in my case, I've seen enough muffins that I can tell it's definitely not a muffin, at least. And then I make that distinction. But if we were to do this in a classical development way, it would look something like this, like pseudocode for distinguishing between chihuahuas and muffins. And this is kind of what, like the rule-based engines that we used way back in the day. I used to do AI like 20 years ago in college, which kind of dates me and tells me how old I am. But then I did something like this. I created rules. But there are a couple of problems with this. The first one is that picture contains is an insanely hard piece of code to write if you're not doing machine learning. And I can't spell chihuahua, which is another problem. But the other problem is that when you're faced with something like this, suddenly all rules break, right? So instead of doing like the rules-based engines of the past, we need to have machines learn more like humans. So the way we do that is we throw a lot of pictures of chihuahuas at the computer and a lot of pictures of muffins at the computer, and we label them and say, these are chihuahuas and these are muffins, and then have the computer figure out the pattern. Usually when it comes to images, it's done with neural networks and things. And it turns out if this is the only thing you want to do, then this is a problem that's already been solved. It's been solved in many ways. One of these ways is through Azure Cognitive Services, where you can just like send in a picture of a chihuahua, and it will tell you all sorts of things, like it's indoor, it's brown and white, it's cute, like it even has feelings. And it tells you all this with a certain degree of certainty. So a lot of machine learning problems have already been solved, and you should look first and foremost at something like cognitive services to see if your problem has been solved. And in that case, it's just an API away. So some of the problems that have been solved are like face recognition, for example, or sentiment analysis. If you're trying to sell a phone, trying to figure out if it's top-notch, then send your Twitter feed through sentiment analysis, and suddenly you can find out if people kind of are happy about it or sad about it. So sentiment analysis kind of calculates like, are the people generally positive in this text or negative? Or even in faces, it can go through and do that. But then there are some that are kind of data specific that you need to solve yourself, and that's the kind of problem we're going to talk about today. So what we're going to do, or my plan for the next sort of 40 minutes or so, is to go through a machine learning scenario and kind of all the pieces that goes into machine learning and kind of talk about and kind of reason about them, but without actually using any tools. Instead, we're going to do it all manually or all in our brains. So in Sweden, where I come from, it's almost a national sport to go to house showings and look at houses and kind of like there's open houses that everyone goes to. Sometimes I go to like 6 open houses a weekend until I had an intervention and wasn't allowed at any house showings anymore. And then I decided that all this stuff that I've been gathering, because I gather a lot of data, I'm kind of like a big data nerd. I've gathered a lot of data about house sales. And if I can't use them to kind of indulge in going to house showings, then I should use them for science instead. So what I did was, and this is just part of the data, I created a set with a bunch of features around the houses that were sold in my neighborhood. And in this case, we have the area of the house in square meters, and then we have the price of the house. And I'm trying to here figure out the price of a house given a square meter. So if I want to buy a 150 square meter house, then how much will that cost? So the first thing I do is gather the data, of course. And I've gathered it manually, but I've also screen scraped from some of the home selling sites in Sweden. The next thing I do is I try to reason about the data and kind of look at the validity of the data and kind of like how it compares to how actual the features I have coming in are good at giving me the answers. So in this case, I plotted like the area versus the price. And this plot that we see here is called a scatter plot. This is something that you see a lot when you're doing something called exploratory data analysis. Like when you kind of visualize the data. So I've visualized the data here, and then let's see, we'll take someone on the first row. So how much is a 150 square meter house? Like you. I'll pick you out. You. 6 million, okay. Yeah, and how did you come to that figure? Yeah, okay, so I think what you did was you did machine learning in your head. And machine learning in the sense like you created a model that is basically you figured this kind of has a trend, and then we can see if we have a trend, then 150 square meters should be somewhere around here. So what you did was something like this. And this is actually a machine learning model based on an algorithm called linear regression. This is the simplest of machine learning models, where we just kind of like try to fit our data into a mathematic equation, sort of, and out comes a line that we can then use to estimate an answer. So 150 comes up to here, so we're around 6.2 million. We're pretty good. Now, when you do machine learning, you have a lot of these algorithms that you try on your data, because not all data is like this, kind of like a linear thing, so you might use other ones, and I'll talk through what some of the other ones are. But this, what we did, is called creating a model and fitting it to the data. So you fit a line so that it kind of fits properly to there. The next question is, because we're kind of making a guess, right? All machine learning is doing is making a guess. It guesses that it was a dog, it guesses with some certain confidence that this person was happy or not. We guessed with some certain confidence that a 150 square meter house was 6.2-ish million. And that confidence is called a confidence interval. And in the manual sense, what we can do is we can use a marker to kind of just plot over the lines or draw over the lines. And that will tell us how good our guess is. Because how good our guess is basically going to tell us like if this is going to be a usable thing to actually make guesses from or not. And in this case, we see that we're kind of like 500,000 off. Like in the sense like we're guessing pretty good, but we could be 500,000 off, which in zlotys is like 250,000. So it's a fair deal, so we have to kind of clean it up somehow to get a better estimate of what the house price is. And to get a better estimate, what we do then is we add more information, because obviously for a house, not only the area affects the house price, but maybe the location of the house, or whether or not it's nice, did it have a roof renewed and all that stuff. But what we've done here is we've gone through the whole machine learning process. This is all machine learning is about. So you go through, you ask a sharp question. In this case, we asked the question, how much is a 150 square meter house going to be? We collected data. We explored the data to kind of see what algorithms would fit the best. We cleaned data, so in this case I had one that was listed as $40 million, or 40 million crowns, which is insane, so I just removed the zero because I wrote it down wrong. And then you can also go in and transform features. I'll talk about that in a little bit. We selected an algorithm. In this case, we selected a straight line, linear regression. We train the model, so we fit it to the data, and we use the answer to get the answer. Now, this is a very simple example. Obviously, there is more to it than this, or else you just go and do machine learning, you know? This kind of machine learning you can do in Excel. What I'm going to go through is essentially like a few of the finer details of all of these things. So, asking a sharp question. There's 5 questions that you can ask machine learning. That's it. There is like no magic going into this. You can either ask it how much or how many, like a regression problem. So these are called regression because you're asking for a number. Like, what's the stock price going to be on Monday for this stock? Or what's the temperature going to be? Or how many people are going to buy my product? And then we have another one, which is classification. Is this a chihuahua or a muffin? Is this email that just came in spam or ham? Is this person with these symptoms? Does she have diabetes or does she not have diabetes? Should be checked out by a doctor. Or it could be a multi-class classification, which means that you have multiple classes that you want to classify it with. Like something like, which topic is this news article? Is it music or politics or sports or technology or whatever? So those are the 2 most common ones that you'll run into. And then we have a special case of the classification, which is called anomaly detection. So anomaly detection is this weird? Like, we have a ton of really good, like a ton of good transactions, good bank transactions, and then once in a while we get a fraudulent one, but how do we know which one is weird? How do we know which one is fraudulent? Or for example, if you look through your internet logs and want to know which one of the requests that come in is like not supposed to be there. And the reason why this is different is because you use different types of algorithms for anomaly detection versus regular classification, because the amount of the thing you're trying to predict, like the amount of the anomalies, is so small compared to the real data set. And then so all of these are something called supervised learning, which means that we have data where we say, these are the inputs, this is what I got as the output, and these were the inputs, and this is what I got as the output. Then we have something called unsupervised learning, where we don't actually know the answer we want to say. So in this case, clustering is a non-supervised learning thing, which is which groups. So what we do here is, instead of actually saying, you know, I want to categorize these products into laptops and mobile phones and this, that, and the other, saying exactly what groups we want, we say, I want to categorize them into similar things. And when might you want to do that? Maybe when you want to recommend something to someone, you want to categorize similar things, like this person might also be interested in this because they were interested in this, but you don't necessarily exactly know what the groups are. Like, you can categorize movies, for example, but you don't have to say they're comedy. They just happen to be similar, maybe because they have the similar set of actors, or maybe because they were similar length, or they were all in French, or something like that, but you don't know the criteria yet. And also you can categorize users as being similar, so you can recommend stuff to people that have similar, like, they kind of look like they have similar ideas about what they like. And finally, there is one that's called reinforcement learning, and this is what you see in self-driving cars, or like automation systems where, like a heat automation system that raises or lowers the temperature to get the temperature right, or maybe a vacuum cleaner that should it continue vacuuming or should it go back and charge? And the way this works is through another thing that we humans are pretty good at, and that is, let's say you're a child and you touch a hot stove, and you go like that, and you realize that I should probably not touch anything red or hot because it hurts. That's the way reinforcement learning works. You do something and you either get penalized or you get a pat on the back saying continue doing that. And the more you get a pat on the back, the more you're going to continue, and the more you get penalized, the more you're not going to continue. So those are the 5 questions that we can ask. And then we go about collecting data. So obviously there's plenty of ways to collect data. I'm not going to go through it, I mean, with sensors or scraping or whatever. But I wanted to show 3 that are in, like, Kaggle is a site where you can download data sets and you can actually go through and compete in machine learning if you want to. But it's a very good site for you if you want to start off in machine learning and kind of get some training data, because there's also a lot of people there that will tell you how they thought about it or how they reasoned about the data and how they did machine learning on it. UCI is another site where you can find old data sets, like usually they're like, say, if it's house prices, it's going to be house prices from 2014, so not relevant, but still good for learning. And Azure Machine Learning is another one that has good data sets for you to practice on. So you can get, like, all sorts of things, like who survived the Titanic, or which wines are good, or UFO sightings that you might want to kind of predict if they are UFO sightings or not. They're always not. So that's an easy prediction, but other than that, we're good. So when you collect data, you're going to collect it in this format, so kind of like an Excel type format. So even if you have multiple tables and everything, you're going to collect them in just one big set. And you have a target. This is for supervised learning. So something, this is what you're trying to predict. And then you have a set of features. So this is kind of your input data to your API. And then you have, like, every single row is one instance or one observation. So in this case, every single row is one sale with information. So these features can either be numeric, like the square meters, or categorical. And the reason I changed these, or the reason I make a distinguish between these, is because if you have it, like, since it's math in the end, math doesn't understand text. So you'll have to turn, like, categories into ones and zeros in the end. So in a category where you have only 2 things, you might change, like, this category into house or townhome. Like, but you say the category is house and you set it as a 0 or 1. And then you have some things, you have some things that kind of look like numbers, like the zip code, for example, that you want to turn into categories because, and the reason is because otherwise math will, like, the algorithms will kind of try to divide them or subtract them or add them or something. And in the case of a zip code, it doesn't really make sense to add 2 zip codes or compare, like, one is bigger than the other. So in this case, we turn that into a category. So you kind of have to go through the data like that. And when you look at what kind of data you want to collect and the features you want to have in, you want to look for 3 different things. First off, is it relevant? So for a house, the distance to water, at least in Sweden, that's a really big thing. Like, if you're by a lake, it's going to be way more expensive than if not. On the other hand, the number of chickens in Alabama whenever my house was sold, maybe not so relevant, so I'm not going to use that. And these are kind of obvious, but then you have some that are not so obvious, like, for example, the broker that sold your house. Is that going to be important for your house or not? And it turns out that some of these kind of, like, lurking features, we call them, are you don't know the cause and effect, because, for example, some brokers tend to sell more expensive houses. They just gravitate to more expensive houses, so it's not like the broker actually made the house more expensive, they just picked more expensive houses. So you have to be careful about cause and effect in that case. Then they also have to be independent, and for example, so if we have the area of the house in square meters, you don't also want to have the area of the house in square centimeters. And the reason for this is because it doesn't give any more information. And it puts, like, a lot of weight on the area that maybe it shouldn't have. This might seem pretty obvious, but what if you changed, like, the area in square centimeters to the number of rooms? The number of rooms and the area of the house are usually very, very related, right? Like, so at least In Sweden, we have, I mean, it's like 25 square meter per room on average, and that's a pretty straight figure. So if you know the number of rooms, you roughly know the area, and the other way around. So you want to avoid having features that are too similar. We call these collinear features, and specifically some algorithms will not be very happy about these. And then finally, so relevant, independent, and finally we want to have them be simple. So a simple feature is something like this. If you have the GPS coordinate of the house, that might be really useful for you as a person, but it's useful for you because you can translate that into, okay, it's close to a school, or it's close to a lake, or it's close to something else. A machine learning algorithm can't make that distinction, so you have to turn that into a simpler one. So this is called feature transformation, what we're doing here. So you transform something that you have into something that's more useful for the algorithm, like, for example, how far away from a lake it is. Okay, so now we have the data, and now we're going to explore it. And exploring it, you can do that either in Excel or something that you have. The middle one here is Azure Machine Learning, and the left one is Python in Jupyter Notebooks. So in Jupyter Notebooks, or rather in data science, you have two languages that you typically deal with. So it's either R or Python. And the cool thing about Python is one that you probably will use if you're a developer to begin with, because Python is a more developer-like language, where R is more a math-like language. The cool thing about this is that it's interactive. So you write code and you run it in the web page, and you combine it with Markdown when you do data exploration. So for data exploration, you do things like this, where you kind of draw diagrams. So Python is really good, it's really good libraries for drawing diagrams of the different data that you have. So one thing, for example, here is that I drew area versus price, and I can see, for example, that I have a house that's really, really big, 400 something square meters, where everything else is 200 square meters. So that's the kind of thing you look for when you're doing data exploration. Okay. Let's see there. So you explore it, and then you go through. So you go through all the features, and you try to figure out, are they categories, are they numbers, how important are they going to be? Do I think that the area actually does affect the price a lot, or do I think that the monthly fee, if there's a monthly fee like a rent, will affect it a lot or whatnot? And then you go through and you clean the data. This is what I was doing when I was kind of removing that 40 million house. So you look for duplicate observations. For example, if on one of the sites in Sweden where I capture data from about house prices, I could see it was showing both when they sold the house and when they actually finally transferred the house, and those were listed as two different observations. In that case, I have to restrict to only use one of them, because otherwise they might duplicate my knowledge about, or they might put more emphasis on my knowledge about the features in that house. Then you go through and you look for irrelevant observations. So irrelevant observations might be something that doesn't really work with your model. In my case, I had houses and townhomes. Maybe they look totally different. Maybe they behave totally different as far as area versus price, or I don't know, land area versus price, or something like that. And in that case, I might want to separate them. So if I create a model for houses, I create a clean model for east houses and a clean model for east townhomes, because they will have a better prediction. And then I go through and I look at outliers. And outliers is what I just showed, where we have something that's extremely big, for example. That does not follow the pattern at all of the regular house. So I would remove those, because they would totally skew the information. If I try to fit a line and then suddenly I have a dot over here, it would kind of make this to the line, where that dot, if I remove it, it will kind of keep the line more straight like that. And then another thing that's important is, obviously, if we don't have data, so if we have a lot of data missing, like if I was missing a lot of the areas, then I couldn't use that area to predict the answer. So I will have to find some way to clean it up. And cleaning it up when it comes to missing data can either mean removing the whole row or guessing what the value should be. So in some cases, I was missing the number of rooms, but then I guessed them based on the area of the house, for example. And then you might have some structural errors, like, for example, when I looked at a region, the realtors like to type them in very differently, so I have to kind of go through and parse. I'll do something like this. Let's see here, clean. Like I start off with these many regions, and then I go through and I create a function that kind of just mashes them into maybe 10 or 15 regions tops, because I don't want to have a lot of categories that have just a few samples. So this is actually Python code you're looking at here. Okay, so we're going to take and then the data exploration. We're going to take a look at how we go through and clean the data and how we do this transformation. So this is a data set of Supermans and whether or not they wear capes. Super important data set, of course. So what we do here is we'll look at all the features and we say, okay, so the first and last name, they're probably not going to be super important in predicting whether or not they wear a cape, because they're unique, so you can't use that to guess for a new superhero whether or not they wear a cape. Sorry. The birth year might be important, but it looks kind of funky. It looks like the person who entered the data, entered it rapidly. So we need to clean that up into something that's more usable for a human. So we do this to it, just mash it down to a format that's the same for all of the superheroes. It doesn't matter, for example, if there was one that was BC, so we added like a minus in front of it, that's okay, you do things like that. Then we go through the next thing here. So next one is height. It kind of looks nice, but it has a huge problem, and that's it's written in feet and inches, like US feet and inches, and obviously, that is not awesome for calculating. I don't know why they don't go to the decimal system, but since they don't, we have to make it into something that's nicer for the machine learning to actually use. And one way to do that is to transform it into inches. So now we have a number that can actually be put into an equation. For the next one, the birthplace, that's a category, and it's actually quite nicely placed. It's okay in a category to have something like unknown, and in fact, sometimes when you fill missing data for categories, you'll put unknown as a value. And then we have this identity is secret. Now this is what I was talking about with structural problems, because now we have something where it's sometimes Y, sometimes N, sometimes yes, sometimes no, somewhere missing. So now we have to go back to the person who wrote this down and ask, okay, so what did you actually mean when you said missing, or when you didn't fill anything in? And they say, oh, okay, well that means no. So then we'll go through and just clean that up too, with a method similar to the one you saw. We do that for the next ones. Can fly. Alignment, it's okay to have multiple categories, like Selena Kyle is neutral, so she can be in a separate category. And then wears cape, also turn that into a yes and no. This is a long process. This is like 80% of machine learning. It's not super sexy, sorry. This is the life of a data scientist. We call this shaving the jock, because where you start kind of like cleaning, and then you realize that, man, I need to clean this a little bit more, and then you see other problems. And then depending on how you guess your missing values, you might introduce knowledge to the system that it wasn't supposed to have. Like, for example, if we replace all the missing with a 0, maybe that's too telling for the algorithms later. Maybe they were missing because, like, not at random, but because of some information. So you need to be careful when you do this. But this is a huge part of machine learning. Now the next part is transforming features. So we've looked at one of them, like moving a GPS coordinate to a more usable 10 meters from a lake. But another one, and you tend to get into doing like a lot of feature engineering where you try to have the data that you have and kind of cram as much information out of it as possible. So let's say you're selling ice cream and you have the dates that you're selling ice cream. Something more useful than the actual dates might be, for example, is it winter or summer? Because that's probably going to affect the sales of the ice cream a lot. Or is this a holiday? Like, is this a weekend? Or stuff like that, because that's also going to turn. So even if you just have a date, you might have a lot more data that you can feed the algorithms that would be useful for it. So you have to figure out, like, what can I do with this and to turn it into something more useful. Like one example I had was I was working on an HR system to try to figure out if a person would leave or not. And we had performance data of them. And what we did was, for example, we took the performance data that they had and subtracted the average performance in the department to see if that person was like above average or below average in the department, to see if that could actually affect whether or not they would stay at the company. So things like that you can do with feature engineering. Now we get to the machine learning part. Okay. So machine learning is basically, now we have all this data and now we try to fit that model. So we've already seen linear regression. Typically you wouldn't use linear regression by itself. You would use something called like lasso regression or ridge regression if you wanted to do that, which is specializations of the base linear regression algorithm. Another one you can use is something called a decision tree. So decision tree is more like the rule-based thing we saw in the beginning, where if it has ears and eyes and all that stuff, except we don't come up with the rules, the machine comes up with the rules. So that is like essentially what machine learning is, right? The machine comes up with the algorithms, we just tell it, or the machine comes up with a model, we just tell it kind of, we want to use this type of algorithm. So a decision tree works a little bit like 20 questions. So I'm thinking about a person, and you have 20 questions that you can ask me to figure out who I'm thinking about. The first question that you're probably going to ask is it a man or a woman, right? Because asking that question will kind of exclude half the population. You've now kind of like said, okay, so at least it's not these people. I only have half the population left to look for. So you try to kind of narrow it down in big chunks, and that's what decision trees do. So in this case, what we have is we have a data set of, and this is a very basic data set that you get like machine learning 101, of if people are going to play tennis or not given sudden weather conditions. So you can think about like maybe you can use this for whether or not you should have people in the store or how many people you should have in the store. So in this case, what we do is we'll look at the data and we'll say, is there something that I can use here to figure out if they are going to say yes or no? So the yellow ones are yes, and the white ones are no. So if we look a little bit, we can see that if it's overcast, so if it's cloudy, people will definitely play, no matter what. Like no matter what the other parameters are, they will always play if it's cloudy. And then for the ones that we now have left, if we look at the ones that are sunny, how can we tell if it's a yes or a no? Well, if it's sunny and the humidity is high, then we don't play. But if it's normal, we do play. And then we'll go through and do the same thing for windy, or rain. And if it's windy and rainy, then people won't play. And if it's not, then people will play. So now we've created like if-else statements that go through. So this is another way to apply, like another algorithm to apply when you don't have linear data. So this works well on data that's not necessarily aligned like that, but like kind of scattered like this. Another algorithm we can use is again, I have to say, with a decision tree, you wouldn't normally use one decision tree. You use something called a decision forest or a decision jungle, which is tons of decision trees that work together, and then you average out the results from all of them. So that's called an ensemble of algorithms that you put together. Another Bayes algorithm is naive Bayes. And in this case, what we have is we have a bunch of email that we got in. Some of them are spam, and some of them are not. And if we look at the ones that have spelling mistakes, and you single them out, we can see that we have pretty much all of the spam emails had spelling mistakes, and like only a few of the non-spam emails had spelling mistakes. So if there was a spelling mistake, how likely is this to be a spam email? Okay, it's 75%. And then we go through and we say some other features, like does the email contain the word sheep? Does the email have no title? Is the email from this type of domain? Is the email, does it not have your full name or whatever? And then you look at all those probabilities and you compare, like you combine them together, and that algorithm is called naive Bayes. Then we have another one that's called logistic regression. So even though it's called a regression, because it's, well, you'll see in a bit, it's used for classification. So here we're trying to classify apples versus oranges. And how can we compare, like how can we divide the apples and the oranges? We have the acidity and we have the sweetness. Any guesses, like what we could use to divvy them up? Maybe a straight line. That's where the regression comes from. Yay. Yeah, or clustering actually, but clustering, in this case we do know that we're looking for apples and oranges, so we're doing classification. We could actually be doing clustering. In that case we would get two groups, but they wouldn't be labeled. And we're going to say, okay, so these fruits are kind of similar, you know. In this case, we're going to use logistic regression, which is essentially kind of like, instead of creating a straight line to predict an answer, you create a straight line to divide between apples and oranges like this. And of course, this is used like with two features. When you have 100, you're instead talking about like a hyperplane somewhere. Like if you had 3 features, you would have to have a straight line or a straight plane. And if you had hundreds, you would have to have a hyperplane, and suddenly your brain would go, and then you would have to use a machine instead. But sometimes the data is not linear like this. So this is quite linear, so it's nicely cut by a line like that. But what if the data looked kind of like this? So you had more, well, first off, in a case like this where you have data that's not linear, you could use a decision tree. Because you can say, okay, so if sweetness is lower than this, and or if sweetness is higher than this, but acidity is lower than this. So you can create rules like that. That's how a decision tree would look. But in this case, you could also use something called a neural network, which is you take smaller algorithms, like logistic regression, like you use that as the activator method, and then you would instead do 2 lines, or actually multiple lines, kind of like ninja cutting off the data. And you would do something like this. So you start off pouring in, like, if it's above or below this line, like if it's above this line, then this is true. And if it's above this line, this is true. And then you take the true and the true and put that in like an AND gate and pass it into the next one, and then it's true for the next section. So that is how neural networks work. Like they take smaller algorithms, combine them together with ANDs and ORs, and then you get an output. Kind of like your brain works with perceptrons, where you get input and you just pass on like a little true or false. And obviously, like a neural network with these 2 doesn't make sense. Normally you have neural networks that are super large. So one thing with neural network is that they're really nice because they can kind of figure out relationships that you would normally not figure out. But a little bit of the danger with neural networks is that you don't necessarily know exactly what it did. Like, you can't figure out like why it made the decision it made. So maybe it made a decision on the wrong premises, and that's actually a big issue in machine learning, where you don't have traceability in your machine learning. But that was the neural network. So how do you know which ones you should choose? Well, luckily there is like a ton of cheat sheets on the web of which ones you should choose. So this is one for Azure machine learning, but it kind of looked the same. Normally in Python you would use something called SkyKit, and they have a cheat sheet. So if we look at something like classification, we'll say, okay, so we're going to predict a category. In fact, are we going to predict 3 or more, then go here? Or are we going to predict 2, then go here? So it's either a Chihuahua or a Muffin. And then depending on how many features you have, or if you want to be fast training, or if you want to have more accuracy, you pick different ones. But in reality, what you do is you take maybe 10 that seem fairly good, and you spot test them on the data, and you try to figure out which one of these seems the best, and which one of these should I now start optimizing. And you'll usually end up with like a random forest for classification, for example, or a neural network, or a boosted decision tree. But depending a little bit on what you want, you might end up with some other ones. So then you go through and you train the model. And training the model, you can do that either in Python, and this is an example of what it would look like in Azure machine learning. I'll just show you so you can see it here. So this is an experiment in Azure machine learning. Azure machine learning is something you can try. It's free to try, and you can do like 1-hour experiments with it without doing anything, like without paying anything. And in this case, for example, if you do classification, you then go and just drag an algorithm out like that. Like, so it's kind of like a drag and drop surface where I've dragged my data. I, in this case, trained it with a linear regression and decision forest, and scored it and tried to evaluate them. So what you did is you pull the data set down. You might pre-clean it or clean it in Azure machine learning or in Python. And then you split your data. And splitting your data is essentially like, so you take one piece for training and one piece for testing. And the reason you do that is because you want to kind of verify how good your model is. Because sometimes you might end up with a situation like this, where should I use a straight line or should I use this really weird curve for this? And if you just look at the training data, you might say, well, you know, that orange curve, it'll really, really look good. But if you look at new data, that orange curve is going to be horrible, right? So it's not going to predict new data very well. This is called overfitting, when you create an overly complex model that doesn't really like fit to new data. You might also say that the line might be a little bit too simplistic, so that's called underfitting. And all of these are things that you find out with training and test data. So, where do we go? Okay. So you clean the data, you split it into train and test, you train the model by picking like your algorithms, and then you go through and score the model. And scoring the model is essentially just the training, like the model saying, this is what I guessed, and pointing out everything it guessed. And then you evaluate the model and you kind of compare what it guessed compared to the real answer. And then you try to figure out how good your model is. So your model, if it's a regression model, we saw that confidence interval, and we can use that. Like, you can say, okay, so I know it guessed 100K for this house. It was supposed to be 120. Then I'm obviously 20 off, and you can kind of average those out and say, on average, I'm like between 10 and 20K off. That's good enough for me. For a classification problem, like whether it's ham or spam, you have a different thing, and this is called a confusion matrix. So a confusion matrix basically says here, actually, like, these were spam and these were not spam, but on the other end, I predicted that I should send them to the spam box or to the inbox, right? So we have 1,000 emails in total, out of which 270 were spam, and I sent 130 to the spam box. So accuracy means how many did we guess right? So we guessed 100 spam that we sent to the spam box, plus we guessed 100 ham that we sent to the inbox. So 800 out of the total 1,000 I guessed completely right, so 80% was my accuracy. Now, this might seem like all you need, but if you look at something like a fraud detection problem, you can guess always that this is a good transaction. Like, let's say you have 99,000 good transactions and then you have 2 fraud transactions. If you always guess right, you will obviously be like almost 100% correct, but you will also not guess any fraud transactions, which kind of limits the usability of your model a little bit. Quite a lot, actually. But so that's why we have 2 other features that we can look at. And the first one is precision. And precision is how many of the things that I sent to spam were actually spam. So am I worried about that I might send like real emails to the spam box? This is a real problem this is a bigger problem if you send real emails to the spam box than if you send spam to the inbox, because I can clean a few of those. I'm good as long as but you don't want like a mail from your boss to end up in the spam box. And then on the other hand, you have recall, which is essentially out of the ones that were spam, how many did I send to the inbox instead, or how many did I send to the spam versus the inbox? And you have to kind of figure out which one of these is important for you and optimize for that one. And then you can do that in here. So, and finally, use the answers. So in Azure Machine Learning, you can quickly turn it into to a web service that you can either call directly as an API, or you can call it from Excel and kind of bombard it with data, and it will kind of batch update your information. So this is it. This is your kind of quick and dirty intro to machine learning. Look at what you want to know, like ask a proper, sharp question. I say sharp because it has to be a question that can be answered with the data, like as a number, as a category, or something like that. Collect the data, make sure you collect the right data, explore it to figure out trends or whatever, clean it, transform features, select algorithm, train a model, and then finally use it, and redo this process over and over again, because as conditions change, obviously you have to update your model. But that's it. So with that, I'm actually done talking, and I think I have like 1 minute for questions, maybe. Thank you. Does anyone have any questions? Yeah, okay, sorry. Okay, so with data cleaning, is there ways that you can include distortions to the data set? Definitely, yes. So you just have to use common sense. So in the case I was talking about with the HR predictions, in cases where they didn't have any performance data, initially we just said 0, which skewed the data a lot, because it turned out that a lot of the people that had left didn't have any performance data. So, and that will, of course, now the model can use to guess that they left because they didn't have any performance data. So you have to be very careful. And that's one way that humans actually create bias into the machine learning process, which is a very dangerous thing. So yeah, just think about it a lot, I guess, is the answer. No, there is no real good automatic way of doing that. Okay, well, I'll be around for a little bit if you have more questions, or if anyone wants to speak up. Okay. Yes. Yes, so Azure ML Studio. So And the way it works is essentially, so with anything, so with Azure ML Studio, it's used to do machine learning with data that you have in Azure. Or you can upload like CSV files or something like that. But essentially, it's just like a drag and drop situation where you go through in sort of like you spot test your algorithms. There is modules for doing parameter sweeping. So once you've selected your model, you might want to optimize it a little bit. And you can do that with parameter sweeping. So essentially, like it's got everything you need to do machine learning, but if you want to do something a little bit more finely granular, then you might want to go into something like Azure Machine Learning Workbench, or work directly in Python notebooks. But Azure ML Studio also comes with Python notebooks, so you don't actually have to install Python to do, like it's basically your end-to-end tool for doing machine learning, or for at least doing prototyping for machine learning. Was that a good answer? Okay. Thank you. Appreciate it.